Hello everybody, Leela Fries here with a presentation on ZOS storage performance and replication analytics. Although some of the material may be familiar to you, I believe you will find several tidbits that will be very helpful in your everyday job. I have 23 years experience in the storage performance trenches. Before joining IntelliMagic, I was the team lead in development for enterprise storage product performance at IBM. Now I am a senior consultant at IntelliMagic for both ZOS and distributed performance. Here is what we will cover today. I will start off with some background material on ZOS storage architecture and how it relates to performance. Then I will talk about some basic ZOS performance concepts, including response time components, I/O rates, and throughput. Next, I will discuss how to be more proactive when monitoring storage performance. Finally, I will review some techniques for finding bottlenecks in a storage system and draw some conclusions. So what is the only correct answer to any performance question? It depends. Almost every performance person I know has used this line to answer a performance question more than once. The sad truth is that performance is part art and part science. Although everyone wants simple rules of thumb, sometimes relying on these too heavily can get you into trouble. That is why effective performance analysts know what factors performance depends on and can look under the covers to get to the real root of the problem. If we look at modern enterprise disk storage systems, we see that all the vendors have pretty much similar architectures. They all have front-end adapters, sometimes called directors, to attach hosts or other storage systems, back-end adapters to connect to drives, either disks or SSDs, large cache memories, and a fast interconnect bus or switch to tie it all together. All the vendors keep 2 copies of modified data in memory for resilience and use RAID at the drive level to provide redundancy. If we go back to the disk storage architecture of the 1990s, we saw a great deal of serialization. This meant that as the storage became more utilized, we would see gradual response time growth, and that would help us to detect bottlenecks. With modern architectures, parallelism is everywhere. This keeps response times low until we reach a critical point when we will typically see a large spike. This makes high response times less useful as a proactive measure of storage health. For those that are new to ZOS storage performance, response time components may be a bit mysterious. This table explains the components in familiar terms by comparing to a telephone call. IOSQ represents time that the device is busy servicing another I/O. PAVs have introduced additional lines of service, so we don't get so many busy signals anymore. Pen time means the phone is ringing, but nobody's answering. For example, the storage system is busy servicing other I/O, so things are backing up. Connect time is associated with actual transmission of data, which is akin to talking on a telephone. Finally, disconnect time is associated with retrieving data from disk. This is comparable to putting someone on hold while you're looking up information. I/O rate and throughput are 2 ways of looking at how much work a disk system is actually doing. I/O rate is the metric most frequently reported, although throughput is generally a much more useful metric. But I/O rate is what most RMF reports provide. In addition, storage vendors typically use I/O rate measures when they're marketing their product. However, throughput gives a much better picture of how much work your storage is actually doing. Here we see 2 charts using real customer data. The first chart shows I/O rate and response time. There is not much correlation between those metrics. The second chart shows throughput and response time, and you can see that these metrics are much better correlated. At IntelliMagic, we see lots of storage performance data from numerous customers using disk storage from every vendor. Typically, the performance bottlenecks we see fall into 4 categories: front end, middle layer, back end, and peer-to-peer connections. The front end refers to the host adapters and ports that connect the storage to the ZOS hosts. The middle layer is the cache, processors, logical structures, and interconnects that exist between the front end and the back end. The back end includes the device adapters and physical drives that store data. Finally, the peer-to-peer connections are connections between disk storage systems that are typically required for remote data replication.
This is just a brief overview of what we will be discussing in the actual video. If you would like more detailed explanations, as well as more content, please follow the link in the annotation.